Thanks for the introduction. Hi, I'm Zhongyi, and I'll present the Preguss. It analyzes, it specifies, and it verifies. This is the joint work with Tengjie, Mingshuai, and our other collaborators. It is often said that program synthesis is the holy grail of computer science. In this talk, we explore what is the holy grail of formal verification. Typically, formal verification acts like a complex machine. It takes programs and specifications as input and output a simple yes or no. To achieve this, many specific methods have been developed. In this landscape, verification power generally increases from bottom to top, while the level of automation decreases from left to right. Our work focuses on two key methods: sound static analysis and automatic theorem proving. We ask, how can we improve their automation and scalability? Okay, I'll change it. Here, I will introduce a synergistic framework that combines the strengths of both, achieving powerful automation and scalability. Let's see how our framework works. We start with static analysis. Consider a program with a function that returns the absolute value of x. Suppose we want to check for runtime errors. A sound static analyzer such as pharmacy RTE can generate an assertion before line 1. This assertion states that if the predicate phi1 is violated here, for example, x equals to int min, then an integer overflow will occur. However, due to the abstraction, the alarm can be a false positive. An analyst would then need to check all execution traces reaching this assertion is valid or unsatisfied. In this case, it's easy to see that the call at line 2 is safe, while the call at line 3 triggers a real overflow. But what about the real-world large-scale programs? Consider this nuclear power plant software with 17,000 lines of code. SOTA analyzers generate hundreds of alarms. Manually inspecting each one to determine if it's false positive or a real error is not only tedious, but also highly prone to human error. This is where a practical verification paradigm comes in. We use a sound verifier to discharge the false alarms and help identify the genuine errors. To use the verifiers such as pharmacy WP, we must first provide specifications. Here, we write a precondition phi2 for the apps function, which requires the input x must be larger than int min. By assuming this precondition holds, the assertion phi1 is verified to be valid. We mark a specification as green if it is verified, otherwise it is red. Then at each of the call sites, like line 2 and line 3, the verifier checks whether the precondition phi2 is satisfied. In instance, these preconditions act as guard assertions at every point where the function is called. For the call site at line 2, since 42 is larger than int min, so the precondition phi2 is satisfied. But for the call site at line 3, the precondition phi2 is violated since the input equals to int min. So an alarm is reported here, and a verification expert have to identify whether it is a false alarm or a real error. Now we have present the workflow of this synergistic verification framework, which combines static analysis and deductive verification. The core problem is, for RTE freeness verification of real-world large-scale programs, the specifying stage still relies heavily on human expertise. To mitigate this problem, There are a lot of recent studies focusing on utilizing LLMs for automated specification synthesis. The common idea is a guess and check iteration framework. First, in the guessing phase, an LLM is prompted to generate candidate specifications for a given program. Then in the checking phase, a verifier validates these candidates. If verification fails, the invalid result is fed back to the LLM to generate new candidates. This loop continues until a valid specification is found or a resource limit is reached. However, this method exhibits scalability limitations when applying to large-scale programs, primarily due to two bottlenecks. First, these methods often feed LLMs with the entire program as context, which may exceed the model's context window limit. Second, and more subtly, these methods struggle to synthesize fine-grained interprocedural specifications, which are essential for scaling verification, but are harder to generate. Let me clarify this point. First, what are interprocedural specifications? Consider the program with its core graph. The function main calls the functions 1 and 0, and both of them call the function ID, which simply returns its input x. At line 1, the return value of ID1 is used as a divisor. A static analyzer may raise a false alarm 5-4 here, warning that the divisor could be 0, which is obviously impossible. An ideal way to discharge this false alarm is writing a post condition 5.5 for function ID, which states the return value of ID equals to its input. With this post condition, a verifier can prove the divisor x is actually 1, thereby proving the RT assertion 5.4 is valid. So here is the key insight. For programs with complex core hierarchies, verifying properties such as 5.4 in function 1 requires specifications in different functions, such as 5.5 in function ID. These are so-called interprocedural specifications. Generating such interprocedural specifications is hard for existing LLM-based methods. Some are limited to intra-procedural specifications of certain categories, such as loop invariants and assertions in individual functions. While other methods can generate interprocedural specifications, but they treat them as a holistic block without modeling their inherent differences, which leads to problems. As subfigure D shows, if an LLM sees the alarm in function 1, it might be misled and generate a precondition 5.6, stating its input cannot be 0. This is a typical over-constraint precondition, since function ID can accept any integer. Remember that the preconditions act as guard assertions and checked at all core sites. This over-constraint precondition induces a new false alarm in function 0 at line 2. Because 0 is passed as input into function ID and thus violates 5.6. This demonstrates how LLM hallucinations can introduce over-constraint preconditions and induce new false alarms. So when we back to our synergistic framework, as we just discussed, the bottlenecks of existing approaches can be concluded into two primary challenges. The first is the context length limitation, and the second is the lack of a fine-grained strategy for generating interprocedural specifications. To resolve these challenges, we propose Preguss. It is built on the analyzing, the specifying, and the verifying framework. Our core contribution lies in automating the specification synthesis phase. The core idea of Preguss is simple: divide and conquer. Our framework has two key stages. I will not introduce the details. Stage 1 tackles the LLM context limit. Instead of processing the whole program at once, Preguss decomposes verification into smaller and manageable tasks called V-units. Each V-unit contains just the guard assertion and the necessary program context. So the V-unit is perfectly sized for an LLM. And stage 2 addresses the need for fine-grained specification synthesis. Its main idea is to generate specs tailored to their context. Specifically, for a given V-unit, it generates preconditions and loop invariants for the host function where the guard assertion lies in, such as this function. And for their COE functions, Preguss generates post conditions and loop invariants. And we evaluate Preguss on a module of real-world X509 parser with over 1,000 lines of code and 20 functions. To verify it is free of RT, the developers construct 251 specifications. And Preguss automatically generates 108 specs and verifies most assertions. Ultimately, a human expert only needs to modify 39 specs based on Preguss outputs to complete the full verification. This means Preguss reduced the human effort by 84.5%, demonstrating high automation and scalability. Besides, the entire process takes less than 3 hours and under $4. This is a marginal cost compared to the days of effort that a verification expert would typically spend on such module, highlighting the great efficiency of our framework. Here is the conclusion. We propose the Preguss framework and foresee that by adopting such two-stage divide and conquer strategy, we can pave a compelling path toward the automated verification of large-scale programs. Thanks for your attention.
So thank you for your talk. And I'd like to ask if the specification generated by the large language model cannot be verified, do you make some feedback to the large language model to let it modify its specification, and what form is the feedback?
Yeah, there are many details during the stage 2, because if a candidate fails, then the verifier will return its feedback, such as proof obligation and the verification condition. Then you can use this information to ask LM to write stronger specs.
Yes.
And you can use a chain of thought. Actually, I may prepare some slides of this work. Okay, sorry. I didn't prepare.
Okay.
Do you have any questions?
Oh.
Sorry.
Oh, I see. Thank you. Okay.
Hi. Very quick question. So in your evaluation, did you end up manually checking the specifications to see if they are good quality or something?
Yeah,
similar?
Very good question. And actually, we do. You see, like this X50 parser, the developer write 200 specs to guarantee it's free of RTs. And Preguss generate 100 specs And we, based on these 100 specs, we found that only we need to modify 39. And you can see the combination is much less because we found a lot of redundant specifications in the in this project, because some specs are assertions that that describe the program states of some locations. It is not useful for the RT assertion, for the verification.
Okay, thank you.
Okay, thank you.